Hey there, science fans! Today we're diving into the exciting world of acids and bases. These chemical compounds are everywhere, from the food we eat to the soap we use. They play a crucial role in many chemical reactions that make our world go round. Acids and bases have intrigued scientists for centuries. Over time, different theories have emerged to explain their behavior. We'll explore three major ones: the Arrhenius theory, the Bronsted-Lowry theory, and the Lewis theory. Don't worry, we'll keep it simple and fun. Get ready to unravel the mysteries of acids, bases, and the reactions they create. Fasten your seatbelts, science explorers, because we're about to embark on a chemical adventure. Let's kick things off with Swedish chemist Svante Arrhenius. Back in 1884, he came up with a way to define acids and bases based on what happens when they mix with water. Arrhenius said that an acid is a substance that, when dissolved in water, increases the concentration of hydrogen ions. Think of hydrogen ions as tiny little particles with a positive charge. They're like the life of the chemical party, making things react. Now, bases are the opposite of acids. An Arrhenius base is a substance that, when dissolved in water, increases the concentration of hydroxide ions. Hydroxide ions have a negative charge and love to pair up with those positive hydrogen ions. A classic example of an Arrhenius acid is hydrochloric acid. When HCl dissolves in water, it releases hydrogen ions and chloride ions. Sodium hydroxide is a great example of an Arrhenius base. When NaOH dissolves in water, it releases sodium ions and hydroxide ions. Now let's fast forward to 1923. Two chemists, Johannes Bronsted and Thomas Lowry, decided to expand on Arrhenius's ideas. They came up with a broader definition of acids and bases that didn't always depend on water. They said that an acid is a substance that donates a proton. Remember those hydrogen ions? They're basically protons looking for a party. A base, on the other hand, is a substance that accepts a proton. Think of it like a game of hot potato. Acids are like the players who want to get rid of the hot potato, and bases are the players who are willing to grab it. Let's revisit our friends HCl and NaOH. HCl is still an acid because it donates a proton to water. NaOH is still a base because it accepts a proton from water. See how this definition works even when water isn't the main event? Section 4. Lewis acids and bases electron matchmakers. Our final stop on this acid-base adventure takes us to the mind of Gilbert Lewis. In the 1920s, Lewis, an American chemist, offered an even broader perspective on acids and bases. His theory focused on electrons, those tiny negatively charged particles that orbit the nucleus of an atom. Lewis defined an acid as an electron pair acceptor, and a base as an electron pair donor. Imagine acids as having a little vacancy where a pair of electrons could fit perfectly. Bases, being generous, have a pair of electrons they're willing to share. This definition expands the world of acids and bases beyond just proton transfer. It explains how some substances that don't even contain hydrogen can still act as acids or bases in chemical reactions. Section 5. The pH scale, measuring the power of acids and bases. Now that we've met the major players in the acid-base world, let's talk about how we measure their strength. That's where the pH scale comes in. It's like a rating system for acids and bases. The pH scale ranges from 0 to 14. A pH of 7 is neutral, like pure water. Anything below 7 is acidic, and anything above 7 is basic, or alkaline. The lower the pH, the stronger the acid. The higher the pH, the stronger the base. Strong acids have a pH close to 0, while strong bases have a pH close to 14. Measuring pH is essential in many fields. Chemists use it to control reactions. Doctors use it to understand blood chemistry. Environmental scientists use it to monitor water quality. The pH scale helps us understand the power of acids and bases in our world.